Hello all. Welcome. Yes. Welcome to Studying with Sarah. Okay. I am a TikTok addicted, phone centric loser. And in order to get myself to study and not just scroll and be annoying, I'm going to record it and I'm going to talk to you like I know what's happening. I don't. This information could be wrong. I don't know. What do you want from me? It's for me, not for you. So whatever. So what are we studying for today, Sarah? Oh my God, thank you so much for asking. We are studying cell physiology. I'm in vet school and we're studying cell physiology because we have an exam tomorrow morning. Yeah, it's currently 6:30. We'll see how far we get. So to begin, we are going to be talking about different hormone receptors. So we're going to be talking about steroid hormone receptors, basically, and then how do they move through circulation, what are their targets, what can they be inhibited by, and kind of going from there. Then we'll move on to more specific, like receptor anatomy, if you will, and then pharmacology, shit like that. We'll go on from there. This is not going to make sense, and I don't know what to tell you about that. Sucks. Imagine what it's like being me. So anyway, to begin, we will be discussing steroid hormone receptors. Now, most steroid hormone receptors are cholesterol derived. So cholesterol is your kind of parent molecule or whatever, and based on alterations to cholesterol, we can get steroid hormones and kind of their receptors. So we go from cholesterol, and you won't be able to read my handwriting. I can't read my handwriting. So we go from cholesterol, and this is not the exact pathway, just fucking deal with it. Cholesterol, then we can get to progesterone. That's a big one. She's important. And if you don't know what progesterone is, Google it. But it's important for reproduction. Okay, so we can take cholesterol, alter it to get progesterone. Progesterone can then be altered into corticosterone, which can then be altered into aldosterone. Progesterone can take another route, and it can become testosterone. We've all heard of testosterone, right? Important. Testosterone can then be made into estradiol. Estradiol is also very important. So progesterone, testosterone, estradiol, those are our main sex hormones when we think about them, or what they're usually classified as. To change a molecule like progesterone or testosterone into another molecule, it needs to be catalyzed by an enzyme, typically. It will. For testosterone to estradiol, we are going to throw our markers everywhere, but it is under the control of an enzyme called aromatase. Don't know how it got its name. I didn't fucking name it. Another thing is we can change testosterone to DHT. It's like dihydroxy testosterone or something. DHT is the more biologically active form of testosterone, so it's the one that's going to be doing more shit. So we need to take testosterone, alter it into a new molecule. Sorry, I matched with the hottest motherfucker I've ever seen on Tinder in my area. Whew. And I sent him a message first, okay? So I was being very big and very brave. And if the recording ends very suddenly, it's because he responded, and I thought he did. He hasn't yet. I'm holding out hope, man. Genuinely, I'm holding out hope. Holy fuck. While I write this down, I'll give you a little story, if you will. So this dude is the most hot man that I have seen in a long fucking time. And he is the like hottest dude that I have seen in my area. Within maybe 60 miles of where I live, he is the hottest guy I've seen. I'm like, bro. So just like, help me God. Please, dear fucking Lord. Okay, I need to stop thinking about him. I need to get my doctorate. I need to get my doctorate. Relax. Okay. Ding. So this is kind of what we're rocking with. There's other pathways, or there's other steps to get from cholesterol to progesterone. I don't know them, and I don't need to know them for this right now. I'll learn them eventually. I'm having a stroke. Cholesterol to progesterone. Progesterone can go to corticosterone. Corticosterone can go to aldosterone, which I'm just now realizing I wrote aldostostone. So aldosterone is very important for like kidneys, blood pressure. It's part of the RAS system, which unfortunately I will be talking about a little bit. So this is just an introduction to her. She's a cholesterol-based or cholesterol-derived steroid hormone. So aldosterone is from corticosterone, it's from progesterone, whatever. Progesterone can also go to testosterone. Testosterone can go to estradiol. Testosterone can go to DHT, which is your more biologically active form of testosterone. Cool. To catalyze the change from testosterone to estradiol, we need aromatase. To catalyze the change from testosterone to DHT, we need 5-alpha reductase. Why the long name? I don't know. Now, what's going on in here? This is the Bermuda Triangle, in my opinion. So corticosterone becomes aldosterone, or it can become cortisol. Cortisol acts with a glucocorticoid receptor. Aldosterone uses a mineralocorticoid receptor. Now you're thinking, those are two different things. They are, but not really. Cortisol can kind of sneak its way in and act as aldosterone. So what's to prevent cortisol to act like aldosterone at all times, which is something we don't want, okay? You don't want that. Well, there is an enzyme, it's 11-beta HSD, that blocks cortisol from just kind of sneaking in and acting as aldosterone. So that's just important to note that these cortisol really wants to act as aldosterone, we block that. So that we don't just have like identity theft, basically. Cortisol loves to commit identity theft, and 11-beta HSD does not let that happen. It's a good thing. You don't want that to happen. Or not all the time. So those are steroid hormones. Hell yeah. Not that tricky, no? So, now we know steroid hormones. Sick. What do we need to know now? Great question, sir. So, hormone, what am I trying to say? So receptors, wow. Receptors work by a ligand or an agonist or something, whatever you want to fucking call it, something that binds and causes a reaction, or something that binds and stops a reaction. It depends. So we have different agonists kind of for receptors. A receptor will not respond if some random fucking thing tries to bind. A receptor is very specialized to work with its own friend, okay? And now you're asking, well, how do we get the steroid hormones from the brain or whatever endocrine organ they are produced by? How do we get them from wherever they are to where they need to act? Incredible question. I'm so glad you're thinking of that. We use carrier proteins. We literally kind of take our steroid hormone, which is hydrophobic. It does not like the water. And what is your blood mostly made of? Water. So what do? We just kind of wrap your steroid hormone in a little carrier protein, and that carrier protein shuttles that steroid hormone wherever it needs to go. It's helpful, it's important. There are different types of carrier proteins, or different ones. The main one is albumin. It's going to be your most common protein that you're going to find in the blood. What albumin is going to bind to, it kind of depends. It has a low affinity, so it has a very high binding capacity. So it's kind of inverse. If I had a high affinity, I have a low binding capacity. So high affinity or low affinity just means how specific something needs to be, basically. So low affinity, I'll kind of bind to whatever, and I'll just kind of carry my little mixed group of people or whatever to wherever it needs to go. So albumin, it carries a lot of stuff. Primarily, we think of it carrying aldosterone and progesterone typically. It can carry other things, but that's just kind of what we think of it usually as. And then we have vitamin D binding proteins, retinol, which is vitamin A. We have sex hormone carrier proteins, thyroid, and then we have transcortin. Transcortin carries cortisol primarily. It can carry other things. It will carry a little bit of progesterone and aldosterone if it feels so inclined, but it's not something that it's going to do on the reg, I guess. So carrier proteins, cool, talked about that. What are steroid hormones? Talked about that. Receptor specificity is very important. Now we're going to talk about basic receptor structure. These are just universal general characteristics, I don't know why this is uncapped, that your receptors are going to have, they have to have. They're going to have a ligand binding region, I guess, or domain. They're going to have a ligand binding domain. They're going to have a DNA binding domain, and then they're going to have a transcription activation domain. So, ligand binding. My receptor needs to be able to bind to the thing that I want it to do. So ligand binding, important. DNA binding, what happens is your ligand comes, it binds, cool. Now a little piece of my receptor can go to a specific part on the DNA, and then using the transcription activating domain, it can begin to alter expression, whether that's to increase a product, decrease, whatever. So it needs those three things to do anything. So those are important. We have a few different types of receptor locations. It can be cytosolic, so in the cytosol, or it can be nuclear. Nuclear receptors are going to be things like thyroid hormone, vitamin D, whatever. Cytosolic is going to be your glucocorticoid, mineralocorticoid, your sex hormones, things like that. And then a little about receptor specificity. If a cell does not know that something is around, it's not going to respond to it, right? So I need a specific receptor on a specific cell in order to respond. Sometimes my cell also needs additional proteins or enzymes or whatever in order to actually do anything with that response. So nothing's going to happen unless your cell knows that something is there, basically. Cool. Hell yeah. Moving on. Now we are going to talk about G-protein coupled receptors, or G-protein linked receptors, whatever the fuck you want to call them. G-protein coupled receptors are one of the most common receptors that we see in the body. What they do is incredibly variable because they have a lot of different mechanisms that we are going to talk about. So with G-protein coupled receptors, there are a few things that are basically universal characteristics. So they have 7 transmembrane segments. So my receptor is going to loop through my membrane 7 times. It's called like the Magnificent 7 or something. I don't fucking know. So it has 7 transmembrane segments or whatever. And that just to like anchor it into the cell, basically. I'm sure there's other reasons. That was the reason that I was taught back in undergrad. That's the reason I'm using now. And then, so it has those 7 transmembrane sections, meaning it's within a cell membrane. And then it also has the ability to modulate and link with GTPase. So GTP, just pretend it's similar to ATP. I mean, it is, but it's not. So GTP is going to be your kind of activator signal, basically. It's going to be the energy for your G protein coupled receptor to actually do anything. But with your G protein coupled receptor, we have a couple subunits that are inside the cell at this point. So we have an alpha subunit, a beta subunit, and a gamma subunit. When GDP is bound to my receptor complex, it is inactive. Nothing's going to happen. However, when something does bind, because my receptor has the GTPase capability, it's going to kick off GDP and add GTP. With GTP activated, or GTP added on, your receptor is active. Now we can go to the next step, basically. So, it's very important. This is just generally what we're rocking with. I don't even know if that's 7, I just drew squiggles. So, my receptor, whatever. This is my ligand, agonist, whatever you want to call it. This is my signal. So my signal comes through, and originally I have GDP. That's if I didn't have a signal. My signal's there, now I have GTP. So now my receptor is active. Now what's going to happen, I think maybe I can write upside down. We're going to find out because I don't really want to keep flipping it around. So what's going to happen is my alpha subunit, big dude, my alpha subunit is going to disassociate from its friends. The beta gamma subunit does have some signaling activity, but it's in specific pathways. It's not usually something that we think of as like, ooh, that's something that's going to cause a reaction. It's mostly the alpha subunit. Hey, alpha males, they get it done. Not really. Alpha females get it done. So my alpha subunit has now fucked off, and it's going to go do whatever. What it's going to do, oh, my kitty. What it's going to do depends on what type of G protein coupled receptor. Okay. It depends on what type of G protein coupled receptor I have. I can't write upside down like this very well. So we have GQ, GQ, GS, and GI. I know that GS and GS is a stimulatory and GI is inhibitory. Could not fucking tell you what GQ means. I don't know. Hey, I got no idea. How about that? But GQ, oh, maybe it's just where they act. I don't know. I'm not a fucking genius over here. So, a way to differentiate kind of what receptor we have is through their second messengers. So second messengers are, hey, the second thing that happens. Your first messenger is going to be your signal binding to your, might not be right. Your second messenger is the second thing that happens inside the cell. That's what I'm rolling with. Right or wrong, that's what I'm rocking with. So those vary depending on what we are doing. So with a GQ2 receptor, our second messenger is going to be, it's like inositol phosphate 3, I don't know, and diacylglycerol. So it's IP3 and diacylglycerol. Those two friends are going to target protein kinase C. Kinases phosphorylate things. Phosphorylation can either activate or deactivate a protein depending on what it is, which is really cool because why would anything be simple, right? Silly goose. You want things to be simple? No, this is science. But with protein kinase C, for this specific example that I'm thinking of, we will eventually go through different pathways, whatever, and in this, actually disregard, because I don't know what I was going to fucking say, so disregard completely. So that's GQ2. We have IP3 and DAG as our second messengers. They target protein kinase C. For GQ, we have different second messengers. We have nitrous oxide and cyclic GMP. Nitrous oxide and cyclic GMP go to protein kinase G. Yeah. Then for stimulatory G protein, so GS, we see cyclic AMP increase as our second messenger, which then targets protein kinase A. One thing to remember, if it's cyclic AMP, it's usually going to target protein kinase A. They're like besties, I don't know. So if I see an increase in cyclic AMP, I see an increase in PKA, protein kinase A. So that's stimulatory, it increases, yeah, makes sense. For GI, or inhibitory, I see a decrease in CAMP, therefore I see a decrease in PKA. So that's kind of what's going on with that. Now, I struggle to remember these sometimes, so maybe I should say this. I'm mostly like doing this off of just pure recall, which is why it's so coherent and clearly very well thought out. So I'm trying not to look at my notes because that's how studying in long-term memory works, in case you were wondering. But for the second messengers and targets of things, I do get confused sometimes. So I am looking at my notes, which I ideally would not be doing, but whatever, dude. So for IP3, which is part of our GQ2 pathway, IP3, after it is made, it will go to the endoplasmic reticulum in your cell, and it's going to bind with a receptor gated channel. So it's going to bind to a channel, whatever, and it's going to release calcium from your endoplasmic reticulum. With that calcium, it is going to be bound to calmodulin, and calmodulin is going to then activate different things basically. And in this example, we're causing contraction of, excusez-moi, we're going to cause contraction of a muscle. So IP3 causes release of calcium, calcium causes contraction. Then for diacylglycerol, when calcium is present, so I need my IP3 to work for my DAG to work, yeah? So diacylglycerol with calcium present will, like we said, go to protein kinase C. Protein kinase C will then do a bunch of shit or whatever, and it will eventually phosphorylate this like thing in the muscle, I don't know, and it's going to cause contraction. So they work together to cause contraction. Well, now we're thinking, well, fuck, now my muscle's contracted. Cool. Okay, cool. How am I going to get rid of that? my signal's gonna leave. That's it. Hello. There we go. In this case, for muscle contraction, my signal would be norepinephrine. So my contractions are gonna happen for as long as norepinephrine is bound to my receptor. Once norepinephrine leaves, everything kind of shuts down. My my circa channel, I think it's like sarcoplasmic and reticulum calcium channel, I don't know. It uptakes calcium. So all the calcium that I just released into my cell, circa is gonna like suck it back up, basically. So calcium's gone. So my contractions caused by my pathway with IP3 are done. My diacylglycerol does not have calcium anymore, so it is not going to be causing contractions. So once norepinephrine leaves, things shut off. For the pathway with nitrous oxide and cyclic GMP as our second messengers, we are looking at vascular smooth muscle, so blood vessels basically. So what do these things do to blood vessels? For nitrous oxide, we stimulate, we're causing relaxation by kind of doing like the opposite of IP3. Yeah, I don't know, man. They kind of work together is kind of what I'm gathering here, so that's cool. Yeah, I'm gonna move on from that because I don't know that, and I don't want to talk about it. So there's that. There's that. It was not... Well, you know, we all have to not do well on some exams, and that's okay. That's okay. It's all good, man. It's all good. It's not. I've done fine on other exams, so I can tank this one. It's all good. Then there's something with like enzyme-linked receptors. I'm gonna be so honest, I didn't go to that lecture. I have not watched the recording of that lecture. But I took a lot of like reproduction classes, so I know about like enzyme-linked, and I know it doesn't look like it from the G protein, but I understand enough about G proteins and sex hormones and cholesterol derivatives that I think I can just kind of freeball that. So that's kind of why I'm not too terribly concerned about that. I will review it whenever. So we're going to move on to cell signaling now, which for the first bit that we're going to be talking about, we are going to be talking about inflammation. So what causes inflammation? How do we modulate that? How do we inhibit that? Stuff like that. So for inflammation, we have something called eicosanoids to thank. Say thank you, eicosanoids, for causing me pain and all this other stuff. And inflammation, while it sucks sometimes, can be very helpful. It is a very important biological mechanism that we have to cause inflammation. It's important. Sometimes our body goes a little sicko mode and it hurts and it sucks and you die. Womp womp. But here's what's causing that. Eicosanoids. So eicosanoids is just a group of signaling molecules, basically. How do we get eicosanoids, Sarah? Thank you for asking. Well, we start with our friend diacylglycerol. Yay! And then there's another kind of dude who causes the pathway to start. I don't remember what it is. Because once again, I'm not using notes for this because I've studied this. So it's diacylglycerol and something. We'll never know. We should know, but I don't. So diacylglycerol is going to maybe I should strike from the record that I've studied this. I have. It's just going to take a second for my Brian to think about it. Yeah, so I think we go from diacylglycerol / whatever to arachidonic acid. So arachidonic acid is like the precursor for your eicosanoids. So once we have arachidonic acid from, I think, diacylglycerol and something else, we get like, I think it's technically like prostaglandin synthase something. 1 and 2. Or it's they're your cyclooxanes, so your COX. So arachidonic acid gives you COX. Hell yeah. Or it will give you or it goes through an enzyme called 5-LOX to give you leukotrienes, which is kind of a fun word. So this, hold up. And if you're thinking, hey, I've heard of COX-1 or COX-2, incredible, because they're involved in a lot of things. If you've ever taken Advil or acetaminophen, wasn't that so hard to say? I'm amazing. Acetaminophen, there we go. So acetaminophen, if you've ever taken that, it's going to target COX-1 and COX-2. There we go. So there's another enzyme here. That's kind of legible. Okay, so we go from, I think, this to arachidonic acid. How do we do that? Through phospholipase A. Very important, very important. Remember that, phospholipase A, bong, bong, bong. Phospholipase A catalyzes something into arachidonic acid. Arachidonic acid, if it is under the effect of an enzyme called 5-LOX, we get leukotrienes. If arachidonic acid is under the influence of COX-1 or COX-2, we get prostaglandins or prostacyclins or something else that I can't remember. So we think of this side as systemic inflammation, shit like that. We think of leukotrienes for lung inflammation, asthma, things like that. So whenever we target pain and inflammation, we're targeting this side. Asthma medications like albuterol, I think, and other things are going to target this pathway. So, cool. And the result, leukotrienes, prostaglandins, prostacyclins, those are your eicosanoids. Just kind of, sorry, there was something on my hand. Generally, for now, we just refer to them as COX and LOX. So, yeah. So, now that we know how eicosanoids are made, what do eicosanoids do? Why do we have them? So eicosanoids, as we've already kind of mentioned, are important in inflammation. I need to write this down, otherwise I'm going to forget what I've already said. So it involved in inflammation, whatever. It also causes hyperalgesia, which is increased pain, which you're like, what? That kind of sucks. Yeah, it does. But it's going to cause it, so boo-hoo. So hyperalgesia, it's also going to cause neutrophil and eosinophil activation and recruitment. Those are parts of your immune system, very important. Oh, also mast cells. Those are also part of your immune system. We usually think of them more for like allergic or allergy responses. So there's that as well. So hyperalgesia, immune system response. We also see vasodilation. So my blood vessels are going to get a little bigger. With that, we can see like increased leak from your blood vessels, which is how you get edema or swelling. That's fluid pooling because it's leaking from your vessels, so it's fluid pooling. So you get edema. Kind of contradictory to that. You also get vasoconstriction. Just kind of depends where it is. and at what point in an inflammatory response you're at. Vasoconstriction is going to be, oops, I just stabbed you. Maybe I don't want to open my blood vessels and just lose a lot of blood. So I'm going to stop that. So vasoconstriction, vasodilation, immune, hyperalgesia, then we are also going to get, what the fuck else are we going to get? We're going to get a drink of water. That's what we're going to get while I ponder this. Oh gosh. I'm just going to write inflammation, which, like, yeah, no shit. But what about inflammation? Oh, I remember. We also see, and this is important, a little embarrassing that I didn't think of this, we are going to see our epithelial barrier improve or strengthen or fortify, whatever you want to fucking say, which is very important. We are going to talk about that momentarily, but here's your brief little immune system lecture, or note, I guess. Your immune system, your very first line of defense is your skin barrier. The best thing you can do is keep your skin barrier intact. You fuck that up, then the inside of your body has to deal with it. And I'm just gonna say, the inside of your body, while very smart, is dumb as fuck. Just don't get hurt. Loser. Suck it. That's how you survive. You don't get hurt. Bing bong. Okay, yeah, I just checked my notes to make sure. Those are basically the effects of eicosanoids. Hyperalgesia, increased pain. Immune cell response and activation, neutrophils, eosinophils, mast cells. We get vasodilation and the associated increased leak from our vessels. We get vasoconstriction. We get epithelial barrier improvement. And then we will also get like smooth muscle contraction too, which is related to vasoconstriction, but not always the same thing. Eicosanoids are also associated with they're called like the 4 ors of inflammation. So the 4 ors are going to be rubor, which is redness, due to vasodilation. If I make your blood vessels bigger, more blood's gonna go there. Blood is red, in case you're wondering, so that's why it's red. So rubor, tubor, which is swelling. Why do you get swelling? Same reason you get redness. Your vasodilation. When my blood vessels are bigger, maybe I shouldn't do it like this. No, don't do that. Hey, when my blood vessels are bigger, basically like more water gets pushed out. I don't know. So you get swelling. Calor, heat. We think of that in terms of fever, not necessarily like, ooh, it's hot to the touch. That could also be true. That local heat is most likely just due to the increased amount of blood. Blood is warm. Hopefully your blood is warm, unless you're a lizard. So calor, we're thinking of heat as in fever. Fever is a very important, very powerful immune response. So we have rubor, tubor, calor, and then dolor, which is increased nociception. So nociception is the feeling of pain. So there's like, they say, so what am I trying to say? I don't know. Google nociception if you want to know more. I can't think of how to phrase it. So those are eicosanoids. We have our increased epithelial barrier, vasoconstriction, vasodilation, immune cell recruitment. We can have swelling, shit like that. We have the 4 ors, rubor, tubor, color and dolor, which are respectively redness, swelling, fever, and then increased awareness of pain, kind of. Pain tells you that something's not going well, in case you're wondering. My dad always used to tell me, pain is weakness leaving the body. Not true. Now I have chronic pain. Whoops. So, fun fact. If your body is in pain, something's wrong. And maybe stop doing what you're doing. Or talk to a doctor. I'm not a doctor. Not a human doctor, at least. So, don't talk to me about that. But anyway, those are generally what icosanoids are involved in. Now, we have already established that icosanoids do a lot. Was that all that they do? Hey, I don't know. But what I do know is that when we were talking about like COX-1, COX-2, and then LOX, they have different roles depending on where they are, kind of. So COX-1, we usually think of it in the gastric mucosa, your tummy cells, or we think of it with your platelets, primarily with your epithelial barrier, which we'll kind of go into in a second. For COX-2, we think of this with joints, soft tissue, things like that. Places where usually, like, if I stub my toe, ooh, ouchie, I'm gonna take Advil because it's a soft tissue ouchie, and Advil targets COX-2. I think it does. I don't know. Don't fucking quote me on that. It does stuff. COX-2 is also going to target your platelets, but it's going to cause the opposite effect that COX-1 has. COX-2 then also plays a role in colon cancer. We didn't talk about that in class. I don't fucking know. And then I think it can do something with the kidneys too. So I'm just going to write down kidneys. And then LOX, asthma, basically. So that's it. But how do they do what they do, and why do I give a shit? Incredible question. So, COX-1. In the gastric mucosa, which you're going to get to see Sarah's beautiful drawing skills. And you're going to say, oh my God, whoa, did you draw that yourself? And I'm going to say, yeah. Obviously, it looks great. Anywho, so really quick, what we need to talk about is usually you put things in your mouth to eat. Hopefully. Sometimes those things, they don't make your tummy very happy. We've all been there. It's okay. It happens. So when you get an irritant to your gastric mucosa, your tummy cells get mad. And what do? An irritant is going to come through, and it bothers your epithelial or endothelial layer of your gastric mucosa. When that membrane or that epithelial, whatever, is upset, it's going to increase expression or release or whatever of phospholipase A. Alarm bell should be going off. Remember phospholipase A? Woo, yes you do. What does phospholipase A do? It causes synthesis of icosanoids. What? Yeah, it does. So we increased the amount of phospholipase A because our barrier was mad because you decided to eat 14 Tootsie Rolls. I don't know what to tell you. With increased phospholipase A, we subsequently get an increase in arachidonic acid. Arachidonic acid will then make our two little friends, LOX and COX. In this case, we're primarily thinking about COX-1. So I'm just going to write it as COX-1. COX-1, in your gastric mucosa, its goal is to tell your cell, hey, you're so sexy, don't kill yourself, basically. So COX-1 inside the cell is going to find its friend receptor, who I think is PGE 1? Possibly number 1, unsure. There are many. So I think it's PGE 1. Impossible to say. At this juncture, it is impossible to say. I don't know. I'm not looking at my notes. PGE1 is going to cause a autocrine response, meaning I'm going to release a signal and it's going to act on me. I'm going to jerk off, basically. Autocrine, here's a little side note. Autocrine, jerking yourself off. Paracrine, I'm jerking my neighbor off. Endocrine, I'm having cyber sex, basically. So with my friend PGE1, I am going to, my cell is going to jerk itself off, and it's going to increase the amount of anti-apoptotic signaling. So it's going to tell your cell, hey, this sucks, don't die though, please, you're so sexy. So anti-apoptotic, don't die. It's going to increase that signal, at least. What it's also going to do is it's going to increase the production of mucus in your cells, your gastric mucosa cells. Because in case you're wondering, mucus protects your cells. So I want you to not kill yourself, and I want you to do something to maybe help yourself. So that's what COX-1 does. LOX, however, LOX is in charge of actually dealing with whatever irritant we have ingested, those 14 Tootsie Rolls or whatever the fuck. So LOX, we see it is going to act paracrine, meaning it's going to jerk its friend off. Very good, thank you. So neutrophils, it's going to find nearby neutrophils, it's going to recruit them and say, hey, this fucking moron ate 14 Tootsie Rolls, now her tummy hurts, can you do something about it? Damn. In this scenario, pretend Tootsie Rolls are bacteria. I don't know. So, neutrophils, they are involved in eating bacteria, neutralizing bacteria, basically. How they do that is they make bleach, basically. So don't drink bleach because your body makes it for you. Homemade bleach. So, bleach, in case you're wondering, is like a little bit toxic to you, but we are willing to cause damage to our cells because COX-1 is protecting the cell as we damage it. Does that make sense? So they're in a really toxic relationship. We don't talk about it, guys. So bleach causes oxidative damage. One thing that we're going to talk about eventually is oxygen is the #1 most dangerous thing in the whole wide world to you. And yet we breathe it, mostly. We breathe it, it's in our cells all the time, making bleach, making other shit, and it hurts us and ooh, ouchie, ouchie, ouchie. Whatever. It's important though, so we deal with it. So LOX is going to cause neutrophils to make bleach to kill shit. Cool. LOX is also going to go to my chief cells in my tummy and my parietal cells in my tummy. It's going to tell my chief cells to increase their production of digestive enzymes to chop up and deal with whatever oopsie daisy I ate. Parietal cells, it's going to tell them to increase their production of hydrochloric acid. I'm going to make my tummy more acidic, basically. Which is why we made mucus, to protect the tummy from the literal acid that I just made and the bleach that I just made. Cool. So, that's great. Rock on. But, because I ate whatever the fuck I ate, my tummy hurts, guys. My tummy fucking hurts. So what am I gonna do? I'm gonna take a medication. For this, I'm just gonna say NSAID. NSAID, non-steroidal anti-inflammatory drug, I think. A true NSAID is non-selective towards COX-1 or COX-2, so it's not going to favor one or the other. There are some drugs that will favor one over the other, primarily COX-2. We're going to talk about that in a second. Spoiler. So I take an NSAID because I made a dumb fucking decision, and now my tummy hurts. NSAIDs, however, since in this scenario, they're going to block COX-1. My cell doesn't know, hey, don't kill yourself, please. And I don't know to make more mucus. So that's not great. So this is kind of what we're rocking with right now. I made an oopsie, ouchie, phospholipase A, arachidonic acid, COX, LOX. LOX does this, COX does that. Hey, don't kill yourself, you're so sexy. With NSAIDs, which is going to be in green, hey, sweet pea. With NSAIDs, they're going to block COX-1. They're not going to block phospholipase A or arachidonic acid. So I still have all of that arachidonic acid, but I can't go the COX pathway. I have to go the LOX pathway. So with LOX, all of my arachidonic acid is being shunted towards making bleach, making digestive enzymes, and making acid, all of which cause damage to my cells. I do not have my hey, don't kill yourself signal. It's not decreased. It's not like I shut it off or I turned it down more. It's just not being told, yeah, I know this sucks, you're fine, deal with it. It's not being told that. It has no support system right now, guys. So if you take too many NSAIDs, that's why they warn you that you can get gastric ulcers. So with COX-1 in the gastric mucosa, yes, it will help with pain, inflammation, but it can also cause gastric ulcers. So that's where we're kind of rocking with there with gastric mucosa. Now, for platelets, we are going to have to kind of lump in COX-1 and COX-2 pathways kind of for this to make sense. But with COX-1 and platelets, we think about platelet aggregation and vasoconstriction. Okay, we need to reference the notes. Okay, yeah. So yeah, I was right. Platelet adhesion, whatever. Adhesion and aggregation are very similar concepts, so I'm going to say I was right. And then smooth muscle contraction. Yeah, okay, hell yeah. So, but what? So with platelets, one thing that we need to understand is the constant tug of war between an enzyme or between a signal called PGI2 and TXA2. There are two wolves inside of you. One of them is PGI2 and one of them is TXA2. TXA2 we think of in relation to the platelets themselves. PGI1 is released from healthy epithelium. So in a normal, nothing's wrong situation, I don't have a cut, nothing's going crazy, my PGI2 signal is always going to be, or always should be, stronger than my TXA2 signal. If I stabbed you or something, I have decreased the amount of epithelial cells because I stabbed you. So now the balance is off. I have less epithelial cells, therefore I have less PGI2. I don't necessarily have more TXA2. It's just in contrast, I have more. So TXA2 is winning. Therefore, platelets are being activated, recruited. They're going to aggregate. They're going to cause clots, whatever. They're going to cause vasoconstriction. It's a whole fucking thing. It's actually really cool. I strongly recommend on your own time, not my time, on your own time, figuring out, hey, what? Just go through the pathway. It's kind of cool. Anywho, for TXA2, in the scenario that I stabbed you, we are going to have TXA2 which TXA2 is a G protein coupled receptor. It's just kind of a special one. She just doesn't fit them. She's not like other girls. She's unique. But still gonna kind of do the same shit, basically. Same shit, different story. I don't know. That's not a saying. Is it? I don't think it is. But whatever. But it's going to cause an increase in IP3, which does what? It goes to your endoplasmic reticulum, releases calcium. Calcium then goes and fucks off and stimulates adhesion of platelets, like on itself. So this is the cell jerking itself off. So it's autocrine. Calcium in a paracrine fashion, meaning it's jerking its friend off, will go to our smooth muscle and cause contraction in there. So that's that. So that's TXA2 and calcium involved. In PGI2, in a normal, healthy, chill, whatever, we keep our calcium inside our cell. We don't really release it. PGI2 is a, hey, chill out signal. It's all good. Relax, man. It's all good, man. But in the case of taking a COX, baby, you seen this, ma'am? Hi, love. Okay, this pathway kind of confuses me sometimes because it doesn't make sense. So TXA2, which is under the charge kind of COX-1. So TXA2, we think COX-1. PGI2, yeah, PGI2 is under the control of COX-2. Here's where it gets a little wonky. If I give you a coxib, that is a COX-2, please stop licking me. Oh my God. I love her more than life, but I need her to not sometimes. So if I give you a coxib, a COX-2 inhibitor, what have I done? I have just turned off your hey chill out signal. So I've turned off your hey chill out signal. Cool. I have not done anything to your everybody freak the fuck out, we're gonna clump and we're gonna panic and blah, blah. I've not done anything to that. So I have not increased it, but I have not given the counterbalance, or I've taken away your counterbalance. Therefore, by default, TXA2 wins. So that's not great. I'm going to clot and I'm going to constrict, and so therefore I'm going to clot more. Not good. You usually don't want blood clots in your body, in case you're wondering. And then this is just kind of a fun little fact. So aspirin is an NSAID, but it's slightly COX-1 selective. So if you or a loved one has ever dealt with like blood clots or anything and they tell you to take an aspirin, what this is doing is aspirin is targeting your TXA2, and it's going to kind of block the signal from TXA2 to cause clotting, which is a good and a bad thing, because if I stab you and you are taking an aspirin, you're gonna bleed out, and that's not ideal most of the time. So that's kind of how that works, in case you were a little curious. So yeah, so COX-1 / COX-2 inhibitors, also known as NSAIDs, they're going to work to decrease inflammation and relieve pain, but we also are concerned about causing ulcers. COX-2 inhibitors, or coxibs, we decrease inflammation and pain, whatever. We can also cause cardiac issues, and that's because I have just blocked my hey everything's fine signal and not blocked my everybody freak the fuck out signal. So everyone's freaking the hell out when they don't need to. Then with certain patients, you need to take very careful, or you need to be very considerate kind of what is the overall body doing right now. Because if my patient is hypovolemic, meaning my blood pressure is really low, or no, my blood volume is low, hypovolemic, or hypotensive because my blood volume is low, or I'm on something called a RAS inhibitor. RAS functions to increase your blood pressure through your kidneys and whatever. So if I'm on something that's stopping my blood pressure from rising, I'm not gonna give you something that is going to cause like constriction of your blood vessels, because in case you're wondering, blood carries oxygen. So if I constrict your blood vessels when your blood vessels are already having a hell of a time, I'm gonna really fuck you up. And in the kidney, blood flow is so incredibly important. It is so fucking annoying to learn, but it is very important. If you are in a medical field, understand the kidneys for fuck's sake. They are so fucking important. Anywho, I digress. Although I hated learning about, I actually am not digressing. As much as I hated learning about the kidneys, they are very relevant. They are very helpful. Every time I go back to clinical practice and we talk about a certain drug or whatever, I'm like, fine, okay, I guess I realize why the kidneys are so important. Fine, I get it, damn. So, kidneys are important, but whatever. So, what NSAIDs or COXIBs can do is if they cause, if they cause vasoconstriction, meaning I'm going to close your blood vessel. If they cause vasoconstriction, that is going to decrease, obviously, the blood flow. Disregard. I think they're going to cause vasodilation, actually. Let's take a little gander at that. Just because I've already gone down the kidney route, I feel like I need to finish my story. So, yeah, disregard. It's backwards. So in the kidney, if I open my blood vessel coming in to like the functional part of my nephron, the glomerulus, I don't know why I'm trying to dumb this down. I don't give a fuck if you understand it. I need to understand it. So with COXIBs and NSAIDs, they will cause dilation of the afferent arteriole. So we're increasing the size of our blood coming into the glomerulus, meaning Oh, okay, yeah. Well, okay, we need to understand what's happening normally with blood pressure. So with low blood pressure at the glomerulus, we see low pressure as well. That continues through your nephron, whatever, and at the macula densa, which is at your, or is part of your distal convoluted tubule, and it sits like right near your glomerulus. At the macula densa, it kind of works as, or it does work as a sodium concentration receptor, kind of. If your macula densa senses low sodium, because there's not a lot of stuff coming through, so therefore the concentration of sodium is lower than it should be, it is going to go through the RAS system, so it's going to activate renin from your glomerulus, which is then going to cause angiotensin to activate, which is going to increase the resistance in your efferent arteriole, so the one leaving. So I've just caused kind of a traffic jam exiting, so things like before that, they spend more time in your kidney, I think. That's how I rationalize it, at least. Your macula densa with low sodium concentration will also decrease your afferent arterial resistance, meaning I'm going to dilate my afferent arteriole. Yeah, so by dilating my afferent arteriole, I'm going to increase the blood volume coming into my glomerulus, because at the same time, angiotensin 2, which caused my efferent resistance to increase, angiotensin 2 causes aldosterone to be produced, which puts sodium channels on your, I forget which part of the kidney specifically, but it puts sodium channels on your tubes or whatever. With sodium channels, it's going to bring more sodium in. Water has a big fear of, water has FOMO, so water is going to follow sodium. So through aldosterone, we get an increase in sodium and water retention. When you retain more water and sodium, your blood pressure or your blood volume increases, so typically your blood pressure increases. However, if I give you an NSAID and I block your PGE2 signal, I block your renin and I block your afferent arteriole from opening. So, no bueno. So it can cause acute kidney injury in fragile patients. So, all that to say, look at your patient. Think critically for 2 seconds. Like, does that make sense that I did that? The answer is no. Don't do it. Okay. Next, we're going to talk about, well, next we're going to take a little sippy of Dr. Pepper. Okay. Dr. Pepper sippy done. Wrong dude from Tinder is messaging me. Fuck. God damn it. Okay. Anyway, we can't think about him. Men are not important right now. Men have done this exam. I can do this exam. Okay. What are we talking about now, Sarah? Great question. We are talking about signaling dynamics. Ooh la la. So signaling dynamics. I gotta scroll through the beginning because I liked the way my professor phrased what signaling dynamics was. So signaling dynamics is, how do we make sure we have the correct amount of signal, and how do we measure how much activity we have because of that amount of signal? And then this is just a fun little thinking thing. My professor, he puts in a lot of clinical correlations, which is really helpful to see why we're learning about this and why it is important to think these things through. So I'll just read you verbatim the clinical correlation. A dog with pheochromocytoma, which is an adrenal tumor secreting catecholamines primarily being norepinephrine and epinephrine, is being prepped for surgery. A significant danger during surgery is hemodynamic instability due to a massive release of norepinephrine or epinephrine from the tumor. How would we prevent norepinephrine from causing hemodynamic instability? Now, what the fuck is the issue with a large amount of norepinephrine or epinephrine? Great question. It is your sympathetic response. Sympathetics are in charge of jacking up your heart rate because, oh my God, a bear is chasing me, or kind of chilling out. So, if I have a tumor that is just randomly secreting epinephrine or norepinephrine, I get these huge sympathetic bursts, basically, that my body does not need. So, randomly, and this is how like your patient would present to you, you would just get like a heart rate of 220 and a heart rate of 40. Heart rate of 198, 10. Like, it's just so dramatic. That's hemodynamic instability. It's a really nice way of saying, oh my God, what's happening to your heart rate? And that's very dangerous. Now, when I'm doing surgery on your tumor that likes to kill you, I need to fuck with it, and to fuck with it makes it more mad. So how do I not kill this dog? How do I not kill this dog, and how do I try and prevent the tumor from not killing this dog? Or which one's gonna kill it first? Hey, fun game show. It's not a fun game show, actually. But it kind of is. It's not. It genuinely isn't. It's really stressful. Anyway, to begin to think about this, we need to go back to our dear friend, second messengers, which are intracellular messengers, basically. So let's think. If I did not have any second messengers, if I sent one signal, I would get one response. Yeah, 1-to-1 ratio if I have nothing to kind of further my signal. If I have second messengers, my one signal can cause initially one response. That one response can go to 3, go to whatever. We get amplification. So that means my body does not have to secrete as much signal to cause an effect, which is nice. Our body does not like to waste energy. So if I can secrete a low amount of something and get a big response, I'm gonna do that. Another benefit of second messengers is amplification, obviously. We can also get modulation and integration. When I have created a million other steps, if at any point my signal turns off, I can stop and I don't have to continue. Or if something starts to go wrong, I can stop, think, was that right? Maybe not. And we can adjust the plan. With all my steps too, other systems can come in and can kind of piggyback off of the response that's already happening and continue on, which is very helpful. We have just saved our body so much fucking time. So amplification is a very big part of the reason why we have second messengers. I just need to find what I need to talk about, actually. So second messengers, amplification, modulation, integration, very important. Then with receptors, we get concerned about desensitization too. This is why, to give you kind of an extreme example, this is why with addiction, you can start with just a little bit and you feel great, right? It's like that animation with the kiwi bird. We've all seen it. We all know. Incredible animation. Very good message. Have some empathy for people with addiction. It's hard. It's a disease. It's troubling. Be kind to people. Or don't. Do whatever. I don't fucking care. Anyway, receptor desensitization. Why do I continue to need more drug to feel good? This is why. Because the more that I overload your receptor, the less it cares, kind of. But what really happens is your receptors primarily respond to changes in signal concentration rather than absolute concentration. So if I have never, for an extreme example, if I have never done cocaine a day in my life, there is no cocaine in my body, which is true both hypothetically and realistically. It's crazy. So no cocaine. I do a little bit of cocaine. My body's never seen that. That is a dramatic change from my normal concentration, which is 0. So I added a little bit of cocaine to the system and my body was like, what the hell? Dude, that's crazy. And had a dramatic response. Well, now the amount of cocaine in my system is a little bit higher than it was at 0, right? Now the next time I'm like, dude, hell yeah, I want to do some cocaine. I'm going to need to increase the amount of signal, the amount of cocaine that I need to do for my body to react. Because now I have absolute concentration, which my body is kind of like, yeah, whatever, old news. So I can't just take enough signal to meet this. I have to overcome it. Well, now my absolute concentration is here. My receptor is used to this. Okay, now I have to take more. blah, blah, blah. It builds up. It's a whole thing. So that's why your body kind of builds up, gets used to it. Not really. It's just the amount that needs, or the amount of signal you need to cause a change in the concentration of signal is different. I don't remember how I started that sentence, but it makes sense. Just deal with it. So receptor desensitization can either be a fast-term process or a long-term process. Long-term, we're thinking addiction. You don't take cocaine 3 days in a row and then all of a sudden you need a pound of coke. I don't know. It builds slowly. You get it. But there are fast and slow methods for how we get desensitization. Certain drugs cause desensitization very quickly. Other ones do not. A very quick method to cause desensitization and for your own cells to be like, hey, I don't care anymore, brother, is my signal binds to my receptor, causes a cascade of events. And at one point, if my signal is being activated, or if my receptor is being activated for too long, my second messengers are going to be like, girl, working like a dog day and night, hello, you're done. And it's going to make I think it's like a deactivating kinase is what they call it. So they make a deactivating kinase, which tells your receptor, hey, hush, shut your fucking mouth, no one cares. And it's going to phosphorylate your receptor, because that's what kinases do, they phosphorylate things. Makes no sense. So my receptor has now been phosphorylated. I basically just, hush, shut your mouth, shush. That's what your kinase does. Deactivation, I don't know, I don't remember what I said. So that's what it does. With my phosphorylated receptor, a protein complex thing called arrestin recognizes that my receptor has been a little naughty, and it binds to my receptor and can put my receptor in timeout mode. So the first part where I had my product inhibit my receptor, that is, I think that's disabled signaling, where it's just like, no, we don't get to do that anymore. Stop it. That's disabled signaling. My arrestin taking my naughty phosphorylated receptor and putting in timeout is called membrane cycling. Maybe it's membrane cycling. I don't know. So it puts my receptor in timeout after however much time or whatever. My arrestin will be like, all right, you've served your time, you did good. And it's going to let my receptor go back into the membrane. But for that period where my receptor is locked away, I need the other receptors to take the job of responding to my drug or whatever. So disabled signaling is my very fast pathway. Membrane cycling is medium. And then if I keep having to put my receptors in timeout, eventually my body's gonna be like, girl, we're just gonna make less receptor. Hello. So less receptor means less response. If I have less response, or if I have less receptors to respond to something, I need to give more to try and bind to the few receptors who are there. Addiction. There we go. That's how it works. That's how it works molecularly, kind of. I don't fucking know. So that's receptor desensitization. What else? Great question. In fact, we will need to reference the notes. So yeah, disabled signaling, membrane cycling, reduce expression. Hell yeah. Okay, now we kind of need to talk about like math stuff, which, guys, I don't like doing, okay? If I had it my way, I wouldn't have to talk about math. I'm here to do things with animals, not math. I'm not a math girl. I'm not a chemistry girl, if you haven't gathered. So this is challenging for me sometimes. But we need to think about math because it's important or whatever. So we're going to be talking about a Michaelis-Menten graph, if we've ever heard of it. It's all the rage in chemistry and stuff. I don't know. I don't know what Michaelis-Menten did besides make my life terrible, but he does a lot and we think about him constantly. But with this in particular, we are going to be thinking about something called half of Emax, which is the concentration of a ligand, so of a signal, of an agonist, whatever the fuck. The concentration of a ligand needed to get half of the response, or half of the response. So concentration of ligand to get half response. And you might be asking, why half? Well, because like technically Emax is like, it's a hypothetical, it's a theoretical thing, it's infinity. So that's stupid to measure something against infinity. So we just measure it at half. I don't know. You also see it with velocity and stuff, which is also where Michaelis comes back in. So we have half of Emax, and then we have half of we have EC50. EC50 is also a concentration. It is the concentration of a ligand to get half of the effect, half of the maximum effect. So yeah, which to me, when I think about that phrasing, I'm like, is that not the same thing? Response and effect? And the answer is kind of. But another way to think of it is Emax is related to efficacy, how efficient something is. EC50 is related to potency, how strong something is, basically. So with efficiency or efficacy, I need to know how much of whatever do I need to get half of a reaction, half of a response. For EC50, I need to know how strong is whatever I'm working with to get half the effect. That's a poor way of phrasing it. But with EC50, we look at that primarily to see, like first off, how close are we to EC50? Because that's where half of my effect is. So if I'm close to EC50, that tells me like kind of my concentration. You can like figure out drug stuff with it. I don't know. But yeah, so Emax is efficacy, efficiency, and she is exhausted. And then EC50 is potency. So with efficacy on a Michaelis-Menten graph, we see an increased Emax, so increased efficiency. Did I not write this down anywhere? I did. So this is kind of handy because usually if you get a mathematical and like conceptual relationship, they're inverse and it's kind of stupid. But with this, if you see an increase in your Emax, your thing is more efficient. If you see a decrease in your Emax, your thing is less efficient. So that's kind of cool. For EC50, I don't know, just think about it harder. Because if my graph moves to the left, my potency or my thing is more potent, so my EC50 has increased. If my graph moves to the right, my EC50 has decreased. Which is important to know when you're just like looking at a graph, because when I was looking at the practice exams for this class, he just likes to give you a bunch of graphs and say, here's where my original line was, or here's drug A and drug B, which one's more potent, which one's more efficacious, and you have to be able to like think through it like that, which is not that bad, but you know, still. And then one thing that we're going to talk about in just a second is how an antagonist will affect the appearance of Emax and EC50. So just because I already have this written down and I know what an antagonist is, suck it. Emax, we see a decrease in Emax with non-competitive antagonists. Does not matter how much concentration of agonist or concentration of ligand that I add into the system, I can't overcome a non-competitive antagonist. So my Emax is going to drop. For EC50, I see an increase in EC50, so I need more concentration. Yeah, I need more concentration to overcome a competitive antagonist. So non-competitive, you cannot overcome no matter how much agonist you have. Competitive, you can. Sometimes you can overwhelm the troops. So that's that. So now we're actually going to talk about agonists and antagonists. Agonists are a ligand that binds to a receptor at a binding point and causes a physiological reaction. With that, we have measurable efficacy and potency because it caused a reaction. Antagonist, something that binds at a receptor or at a binding site or not, and does not cause a reaction. It inhibits a reaction. So agonist binds, causes. Antagonist binds somewhere, inhibits response. Yeah? There are different types of agonists and antagonists. Agonists, we have a full agonist where my agonist, let's just say, oh my god, he messaged me. Genuinely? Let's fucking go. God damn. Okay, full agonist, guys. We're riled up. We're gonna take a Dr. Pepper break. Hold on. Okay. Full agonist. Yes. Full agonist. Something I give you is just exogenous. If I give you one drug, it is just as good as whatever your body can make. It is the same response. Partial agonist, I give you something and it still works. I still get a response. It's just not as strong as the something that I can make. It's good, it's just not great. A super agonist, and I had to think about it in a stupid way, is God, all I'm thinking about is that guy. Holy fuck. Damn. Anyway, so a super agonist, holy shit. A super agonist is something that I give you that does so much better than your endogenous one. I had to think of it as you get cucked by somebody and he blows your wife away and you're just there like, oh no, oops. So super agonists, they fuck good, and then they make your wife like, holy shit, why'd I marry this bozo when I could have this dude? So that's cool. Or you have an inverse agonist. So inverse agonists do not confuse this for an antagonist, because what? Antagonists inhibit a response. There is no response. Agonist, a response is made. It's just not the one that we wanted in an inverse. So inverse, my exogenous ligand binds and it causes the opposite effect that I wanted. So sometimes that's an oopsie, which we discovered with a drug. We tried to make a drug to counteract alcohol poisoning, and what happened is it had the opposite effect and it made people like very nervous, very paranoid, because it did the opposite of what we wanted. We wanted to make people feel kind of like loosey-goosey so they would not want the like free feeling that you get with alcohol, like when you're all like, yeah, whatever. We wanted to mimic that. Oh shit, I made you fucking terrified. That's not good. That's an inverse agonist. It is not to be confused with an antagonist. Inverse agonists can look like competitive agonists. Competitive antagonists. They are not. Okay? Now, we move on to antagonists. Antagonists, there are less subtypes. They're less special. Remember, antagonist, I bind, I do not cause a reaction. So, the thing is, where do I bind? Competitive antagonists are, I bind where you bind, so you don't get to bind. So, womp womp. So, competitive antagonist, this is my receptor, this is my competitive antagonist. Bonk. Now, my actual agonist, the one who's supposed to go there, it can't get in because something's blocking its driveway. Not great, very annoying. However, with competitive antagonists, if I throw enough agonist at you, eventually your antagonist is going to pop off. Hey, pop off, slay. And I can bind. Or I'm going to throw so much shit at you that I'm just going to overwhelm, and eventually I'll find a receptor or two to bind to. So competitive antagonist, I can overcome. I can still elicit a response. It will not be as strong, it will not be as fast, but I can still eventually elicit a response. Non-competitive antagonists are, fuck your binding site. I don't give a fuck about your binding site. I'm going to cut off your legs. Like, it just shuts down your receptor completely. So it binds at an allosteric site. It's just not the main site, basically. So with a non-competitive antagonist, it does not matter how much agonist I throw at my system, my receptor is shut down. Nothing's happening. So my agonist, it can still bind. It's not going to do anything though. So non-competitive antagonist, I cannot overcome. Competitive, I can, which is why we see a decrease in Emax for non-competitive. So it doesn't matter, I can't overcome that. And we see an increase in EC50 with competitive antagonists. That's why. Another thing that we need to think about is the time that a agonist or the time that an antagonist is bound to a receptor, also known as your K-off rate. There's K-on and K-off. Take a wild guess of what those fucking mean. So we can have a reversible antagonist. So you can have like a reversible competitive or whatever. A reversible antagonist means that there is a measurable time before my antagonist kicks off and goes away. So my receptor can go from being inhibited to uninhibited. Inhibited is the whole thing. I can also have an irreversible antagonist where there is no measurable K-off rate, whether that be it's a I think it's called like theoretically irreversible. No, practically irreversible. Practically irreversible is my antagonist has been bound to my receptor, or it's inhibiting my receptor. It's been bound to my receptor. Holy shit. It's been bound to my receptor for so long that whatever initial reaction I tried to do, my body's like, all right, well, I guess we're not fucking doing that then. And it kind of gives up. So in a meaningful physiological time frame, my antagonist does not leave. That is a practically irreversible antagonist. An actually irreversible antagonist is one that it is covalently bound to my receptor. It has handcuffed it together and it's like, you are not doing fucking anything. So a irreversible, like a genuinely irreversible antagonist, you're not getting that fucker off. Not a chance in hell. Reversible, Yeah, you could. Practically irreversible. I mean, yeah, but not really. Like it's left, but like the damage has been done, so it doesn't fucking matter. So that's cool. So thinking back to our dog with the pheochromocytoma, what do we want to do? We want to give this dog a non-competitive antagonist, right? A non-competitive antagonist cannot be overrun. It cannot be outcompeted or whatever with the endogenous thing that the dog is producing. So if I give you a non-competitive antagonist, whatever you produce cannot do anything, right? Cool. So I'm going to give my dog, I think it's phenoxybenzamine, which is a non-competitive antagonist for, I want to say it's my alpha adrenergic receptors or it's beta. I don't remember. It's one of them. Or hey, it's muscarinic. Unsure. It's a receptor somewhere. So I give my dog phenoxybenzamine, which is a non-competitive antagonist. Cool, my dog's okay, right? No, your dog died. Still, you gave it a non-competitive antagonist. Why did it die? Stay tuned after I text this guy back